Yes, welcome to my talk. My name is Qubits. I'm a master's student from the University of Bremen. This talk will be about equivalence checking of dynamic quantum circuits. It's going to be a quick talk. I'm now also working at a research institute in the DFKI, the German Institute for Artificial Intelligence. This focus, since we are the hardware architecture working group, will be more on how to have like an EDA flow, which means electronic automatic design. So what are the big limitations of current quantum circuits? Well, first of all is the limited amount of qubits. Like IBM has 1,000, but there's still a very shallow coherence, so the qubit states decay very fast, and the gate fidelity is very low. Yes. We can solve this by IBM tries to solve this by introducing a new type of quantum circuit called dynamic quantum circuit. The important thing which happens here is that first of all they recycle qubits. So here we see a Bernstein-Parsilani circuit with 3 qubits, and this can be converted into a dynamic circuit which just has 2 qubits. Here you see that this one is actually this qubit, Q1, which is now moved here. And further, we can introduce further non-unitary operations, such as active reset you see here, or if-else, and mid-circuit measurements. So this motivates the case for why dynamic quantum circuits are important. To reiterate, they solve one of the biggest platform limitations of current quantum computers, and in the best case, they have an n to 2 reduction of qubit that's bounded by the number of entangled qubits. So next, why is circuit verification or equivalence checking important? Well, if you show me 2 different circuits and ask me are they the same, this is a very important question, like if you're designing circuits, since we all need to know that if we optimize something, the functionality remains the same. There's a naive way to test this, which is by doing a proof by negation, so just trying every input and seeing that every input generates the same output for both circuits. This has a bad time complexity and a bad space, or size, like it's both is exponential. We want to use the power of reversible operations, so I think you all know that quantum circuits are unitary, and thus we know if we have 1 and the adjoint of itself, we get the identity. This is what I'll be using. Here we have an example of just 2 C0 gates put after each other, and I say this is equal to an empty circuit. You can prove this by having the first matrix multiplied with the second matrix, and this will be again that. Again, bad complexity, exponential runtime, cubic runtime and exponential space. ZXCalculus is one good way how to solve this. It is a graphical way how to describe circuits. The circuits are described by wires and spiders. You can read my paper or the slides or the Pluto notebooks to get more details. What really matters is connectivity is the only thing which matters. So this is actually equal to this because we just go from here to here, so it doesn't matter if the lines are bent or straight. Most important for ZX calculus is that rewrite rules do not change the unitary map or the linear map as they're called here. So for example, if we have 2 phase changes, we can just sum the phase changes into 1, or we know that 2 Hadamards is equal to this. And by applying all of these rewrite rules, my software also has them in the non-terminating way, but we just stick to these. By applying these rewrite rules, you can take the one circuit and the adjoint of the second one and just rewrite it or simplify it using circuit optimization algorithms. So to prove identity, we just show that we are remaining with bare lines. Here's a small example. So if we have one C0, another one, and another one, this is actually equal to a swap gate. We can prove this by first twisting this one time. It's like a movement like this. Then applying the balance rule and the fusion rule. And then we immediately have proved that this circuit is equal to this gate. Next one, now what about non-unitaries? There are different ways. I decided for my research to do a unitary reconstruction. So given a circuit which is dynamic and contains non-unitaries, such as this reset or the classical controlled logic, I can overcome the resets by undoing the recycling, so moving this back into a new qubit. This is okay, because this runs on hardware, which is constrained by platform limitations, such as the qubit count. This runs on my classical computer, which in the ZXCalculus.jl module, which is very efficient, is not limited by a high amount of qubit. Then I move all the measurements to the end, thus having again a unitary circuit. Here's a small example of the Bernstein-Vazirani circuit, the already reconstructed unitary part, which I merge together here. Then I apply all the rules, and I'm left with only empty wires. Thus, I prove the equivalence between the circuits I showed at the beginning of the presentation. How is this done? First of all, there are many nice libraries from the Yahoo ecosystem, which I'm using. Thank you very much to everybody who contributes to them. Yahoo.QASM, OpenQASM parses it. This library I developed myself, and it soon will be published. It does the unitary reconstruction, and next I will implement the optimization steps. Then it's converted into the high-level intermediate representation, into ZXCalculus, and then we verify the equality, using also a method I implemented in ZXCalculus.jl. There are like 7 notebooks I wrote in the different repositories, so check them out. They're linked also in the pre-talks. Ask me about more, and please ask questions now.
We have 2 minutes for questions. Any questions?
Hi, great talk. So the input circuits, they have to be in like a QASM string format? There isn't like a symbolic language you've made to specify the input circuits?
I use OpenQASM files, since there are many benchmarks that contain thousands of circuits, and my goal is to have like a complete EDA flow, so load the circuits and bring them in. Of course, you can also directly work with ZXCalculus, where you have the push function, where you can push specific spiders onto it, so that should be possible to do it symbolically.
Sure. Because one application I can imagine is you've got a circuit in a conventional gate basis, but you want to check whether it's equivalent to like your really funky esoteric circuit expressed with a weird basis, which unlikely is easily representable in QASM. So would you consider like making support for like many controlled power gadgets or something?
Should be possible. Also, Catherine will be having a nice talk about OpenQASM 3. Which I'm not supporting yet, so I'm looking forward to that as well, and we should talk after that talk about
Sure.
this.
Thanks very much.
Thank you. We will have our next talk. Thanks, Liam.